Well, students, we've taken a look at work, we've looked at energy, and now we're going to look at the Work-Energy Theorem. It's very simple. All it says is that if something does work on an object, then the object's energy is going to increase. Also, if you happen to do negative work on the object, then its energy will decrease. And this might seem very obvious, but 200 years ago it wasn't obvious, and Isaac Newton didn't figure it out. Okay, so now let's talk about how this is going to play out. Let's see here. Okay, so the kinetic energy of an object, we can calculate it. Here's the formula. Kinetic energy equals 1/2 times the object's mass times its speed squared. And we're going to use this for a series of examples, which is going to illustrate the Work-Energy Theorem. So, all right, here's our first example. Lee, by the way, Lee was a little kid down the street, and he was amazing. He could do incredible things on his bike and scooter and so on. So I remember him, and he, every time I think about this stuff, I think of his tricks on his bicycle. So Lee is on his scooter. He's not moving right now. His mass is 35 kilograms. What is his kinetic energy? So, well, you're going to use the 1/2 mv squared formula. His mass is the 35 kilograms, and he's not moving. So his speed, his velocity, is 0. So it's going to be 1/2 times 35 times 0 squared. So his energy is 0. We have units, kilogram meter squared per second squared, which is the same thing as joules. So here we are. Our answer is 0 joules. So now his mom gives him a good push. So now he's going 4 meters per second. Yeehaw! What is his kinetic energy now? So we're going to plug in the 4 meters per second. So it's 1/2 mv squared, 1/2 times 35 kilograms times 4 meters per second. Don't forget to square it, and you get your answer, 280 joules. Okay, so he's gone from 0 joules up to 280 joules. How much work did his mom do to get him moving at that speed? And so now we use the Work-Energy Theorem. The work that she did is the change in energy. He has just kinetic energy. So it's the new minus the old. Remember, change is always new minus old. And so the new energy is 280. The old energy was 0 joules. And so she did 280 joules of work. So that was getting the answer from the Work-Energy Theorem. Now, usually there's another way to get this kind of result. So let's take a look at this other way. It still is pretty much the same example. Lee's mom, though, we're focusing on her strength. She's strong, and she could push with 140 newtons. And she did that over over 2 meters. So how much work did she do? Well, remember from the previous lecture, work can be calculated as the force times the displacement, the applied force times the displacement. So we have that she pushed at 140 newtons of push. The displacement was 2 meters. You multiply and you get 280 Newton meters, which is the same as 280 joules. You get the same answer. And of course, you should. And then, of course, I kind of set things up this way. I wanted them to have the same answer. But in real life, it will be the same answer. All right. So now another example. It's also going to be the work-energy theorem here. So Lee is now at the top of a slope. He built himself a ramp, and he's up at the top of this ramp, and it's 15 meters long, and it has a 40-degree slope. And so now he's rolling pretty fast. After going down the slope, he's moving pretty fast. And the question is, how much work did gravity do on Lee? Obviously, gravity did some work, right? Otherwise, he wouldn't be moving. Okay, so let's figure this out. So we need to start by drawing a free body diagram. So you've got here this dot right here. This is Lee, right there. And the ramp can only provide a force perpendicular to the ramp. Okay, that's the normal force. That's this right here, the normal force. And gravity pulls down. Okay, so here we are. Gravity's pulling down. And in order to figure out how much work gravity did, we need to figure out the component of the gravity that's in the direction of his motion, right? He's moving down this way, so we want the part of gravity that's also down this way. And so what we do is we decompose the gravity, the weight, the force of gravity, which is downward, into a part that's perpendicular to the slope and a part that's parallel to the slope. The part that's perpendicular, all it's going to do is it's just going to cancel out, right? It's going to cancel out the normal force. But the parallel part doesn't get canceled out. It makes him go, right? Newton's second law. And so we have the work that the gravity did is the parallel part of the force times the displacement, his motion down the hill. And okay, so let's see, that's the SOHCAHTOA, right? That's the opposite side. So that's why we have a sine of theta, and the weight is m times g, and the displacement is here. And so we're going to get an answer out of this. 35 times 9.8 times the sine of 40 degrees times 15 meters of displacement, and we get our answer, 3,307 joules. So gravity did work on Lee. Gravity made him go down the hill. Okay, well, so now the question is, how much kinetic energy does he have now? Now that he's at the bottom of the hill, how much kinetic energy does he have? And so we can use the work-energy theorem, right? So the work is equal to the change in kinetic energy, right? That's what work does. Work changes the amount of energy of something. So we have the new kinetic energy minus the old, right? That's a change. And at the top, he was not moving, so he had zero kinetic energy. And so we have that the new kinetic energy is, minus zero. Okay, it's just the new kinetic energy will be equal to the work. But we figured out what the work is. We know that it was 3,307 joules. And so now we know that he's going to have 3,307 joules of kinetic energy. Yeah, okay, now, sorry if this seems stupid or too obvious or whatever, but you got to get a good grip on these ideas because we're going to be using them a lot. This is really the bread and butter of physics right here. Okay. So, okay, now that we've got his kinetic energy, we can figure out his speed at the bottom because we have this formula, right? The kinetic energy is 1/2 mv squared, and we can solve for the unknown. You see, we know the kinetic energy, we know his mass, v is the unknown, so we solve. And so isolating v squared, that's our first step. We have 2k over m. Then we take the square root of both sides, and we have v equals plus or minus the square root of 2k over m. And so we have plus or minus the square root of 2 times the 3307 is the kinetic energy, right? And dividing by 35. And we get that the speed could be either positive or negative 13.7 meters per second. Now, one of these two answers is not going to be right. And depending on how you define your coordinate system, let's say we say the x direction is down the slope. Let's say that's the x direction. So then the one that we want would be the positive answer. The negative answer would represent him going uphill at that speed, but that's not what's happening. So you just have to be aware that sometimes the math doesn't quite match up with the physics, and you have to make a judgment call. You have to use your brain and think about it. And so after thinking about it, you realize, okay, it's the plus answer. That is the correct answer. Okay, so I have a question for you now. Work can be positive or negative, and energy can be positive or negative, and velocity can be positive or negative, but kinetic energy is always positive. Why is that?